Lab 7, Analyzing Motion. In part A of the lab, we're going to be analyzing horizontal motion. So you can see in the picture below, there is a green cart. So that rectangle is actually a motorized cart. It is battery operated, and I'm going to be turning on a switch and showing you the video in a second where that car will be moving along the horizontal. It is placed on the floor in the lab. You can also see that the back end of that cart is in line with a piece of tape that says start on it. So this is the starting point. You can also see that there are other pieces of tape on the floor marking off certain distances. So we have 30 centimeters, 60 centimeters, 90, all the way up to 180 centimeters away. So you can see those distances reflected in the table. So when I start the cart, we're going to also start a timer. And we are going to time how long it takes to go each of those distances. So when the car starts at the start mark, once it hits the first piece of tape at the 30 centimeter mark, we then press the lap button on the timer so that it gives us the time it took for that cart to go 30 centimeters. As the cart continues going, it's going to hit the 60 centimeter mark. To go from the start line to the 60 centimeter mark, it takes 1.73 seconds. The next mark on the floor was set at 90 centimeters. So for that cart to go from the start line to the 90 centimeter mark, it takes 3.05 seconds. So we repeated this again for 120 centimeters, 150 centimeters, and then last 180 centimeters. So these are reflecting the total time taken to travel that distance. We timed the cart with the back end on the start piece of tape, and we stopped the timer when the back end of the cart got to the next piece of tape. We are then going to use the data collected from the horizontal motion to make a graph. So we're going to graph the data present in the table. So how are we going to do that? Well, we're going to take the distance, the total distance in centimeters, and plot those values on the y-axis. Then we're going to take the total time and plot those along the x-axis. So we're going to take this first point in trial 1 and plot that. So notice that trial 1 just has 0 for distance and 0 for time. This is just to ensure that you are going through the origin when making your best fit straight line. And also, if you think about it, if you go a total distance of 0 centimeters, that will take you a total time of 0 seconds. So it is a plausible point. Next, you will plot the second point for trial 2. So to plot that point, you're going to go 30 centimeters out along the y-axis and then follow it to 0.78 seconds along the x. So that will be your first data point. You will do the same for trial 3, 4, 5, 6, and 7. So you should have a total, including the origin, of 7 data points. Once you have plotted your points, I want you to draw your best fit straight line. Now this isn't perfect data, so when you're drawing your best fit straight line, starting at the origin, you will most likely not be able to go through all of your data points. I don't want you connecting the dots. What I want you to do is use a straight edge of some sort and draw the best fit straight line that you can. So your goal is to go through as many points as possible, yes, but it's more important to have the same amount of points above the line as you have below the line. Because essentially what you're doing by drawing a best fit straight line is you're averaging your data. So to get the best average, you need the same above as below. Once you have your best fit straight line, you can then calculate your slope. When calculating your slope, please show your work on your graph. You can see the equation to calculate for slope below. So calculating slope, we are calculating rise over run. So we are doing the change in y over the change in x. More specifically, we will pick 2 points on the line, so make sure they are on your best fit straight line, and you'll insert their values into this equation, y2 minus y1 divided by x2 minus x1. So this y1, x1, that is going to be your values for one of the points that you pick on the graph on your best fit straight line, and y2, x2 will be the values you get from the second point on your graph. Now, what are we actually calculating when we're calculating slope? Well, looking at this, we have the total distance along the y-axis and the total time along the x-axis. When we calculate slope, what we're calculating is y over x. So let's look at the units on that. Y is distance, so that's going to be centimeters. X is time. The units on that are seconds. So the units that I'm going to get for my slope are centimeters per second. Now we've seen something very similar to this in class. Centimeters per second is actually a velocity. Usually we measure velocity in physics class in meters per second. So when we calculate slope, we're actually calculating the velocity of that motorized car. So now we're going to move on to part B, which is ramp motion. So you can see in the picture that we have a board attached to a ring stand being held in place by a clamp. So the reason it's held in place by a clamp is because we're trying to see the motion on a ramp. So it's very similar to part A. We're going to be using that battery-operated vehicle. We are going to be measuring how long it takes for it to go certain distances, but the difference in this experiment is that now we're doing it on a ramp instead of a flat surface. So in the picture, it is currently at the highest elevation that we're going to do. So the data set for the highest elevation is in green. So you can see over in green here, this is the highest elevation. Now, in your lab manual, your data table for part B, along the very top of the data table, it lists the elevations. So this is going to be the 60 centimeter elevation. But I want you to go ahead and cross out that 60 centimeters because we couldn't get the vehicle to actually go up the ramp when it was elevated that high. So you're going to change that 60 centimeters to 45 centimeters because that's the actual elevation that we collected this data at. Once we collected the data at the 45 centimeter elevation, we took that ring clamp and we lowered it down. We lowered it down to 30 centimeters. So this data set in white here, instead of having a 40 centimeter elevation like your lab manual says, we collected the data at a 30 centimeter elevation. Last but not least, the data set in red, we went ahead and lowered the ramp once again to its lowest elevation that we collected data on, and we used 15 centimeters there instead of the 20 that is written in your lab manual. So what we're going to see in the video is how the data was collected at the highest elevation. So when you look at the board that the car is going to climb, you can see there are markings across the board. We have a 0 meter mark where we're going to start the vehicle at. We have a 0.25, a 0.5, a 0.75, and then finally a 1 meter. Those have all been converted into centimeters on your table for you. So when we start the vehicle, we start it with the back end of the vehicle in line with that 0 meter mark. Once we let the vehicle go, we start the timer until the back end of the vehicle gets to the 0.25 meter mark. Then we start at the 0 again and let the vehicle go to the 0.5. Get the time for that, go back to starting, and see how long it takes for the vehicle to go 75 centimeters. One last time for our last data set, we would bring it back to the start and let it climb all the way to the 100 centimeter mark. So notice our very first trial, we have zeros across the board. This is for the same reason that we had zeros in the last one. You travel 0 distance, it takes 0 seconds to do that. We're now going to take this data and plot it on a graph. So how are we going to plot this data? Well, we have 3 separate data sets this time. That's why they're color-coded. We have one data set at 15 centimeters in red, another data set at the 30 centimeter elevation in white, and the last 45 centimeter elevation in green. So you are plotting 3 different data sets. You can plot all 3 of these data sets on the same graph, or you can do 3 separate graphs. That is your choice. So when you do this, it's going to be very similar to the last graph. You're going to have your X and Y axis. You are going to plot the time on your X, just like before, and you are going to plot your distance along the Y. So for the first data set, you are just going to use the data in red. So all of these 3 straight lines that you're going to plot are going to start at the origin. The first data set, data point, you are going to go 25 centimeters along the x-axis. You will follow it over to the 0.68 second on the y, and you will plot a point. So you will only have 4 data points, not including the origin, for each of these lines. So once you plot all 4 trials at the 15 centimeter elevation, then what I want you to do is draw your best fit straight line. So you're going to start at the origin, draw a straight line through as many points as you can, and this is not going to be straight because I'm doing it with the mouse and I don't have a straight edge. So you're going to draw your best fit straight line. From that straight line, you are going to calculate a slope for the 15 centimeter elevation. Okay, so I'm going to call this guy 15 centimeter. Then you're going to go to the second data set. You will plot those points. If you do it on the same graph, you might want to plot them with a different color so that you can keep track of which data points are which. Once you plot those data points, so I'm looking at this set right here, you will then draw your best fit straight line through those data points. So this would be my 30 centimeter elevation. You will then calculate the slope for that line. Your last data set in green here, plot those on the graph in the same way that you did the other 2. Draw your best fit straight line through them, and then this will be your line at the 45 centimeter elevation. So you are going to have 3 different data sets, 3 different best fit straight lines, and 3 different slope calculations. So remember, when we were calculating slope, we said what we're calculating is the velocity of that vehicle. So what you should be seeing is that as the elevation increases, the velocity of the vehicle is decreasing because it's harder to climb a steeper slope. So for part C of the experiment, we're going to use what we called an air track. And that's what this silver thing in front of us is. So for the accelerated motion portion, the lab manual describes a marble run. So instead of a marble run, we're going to be using this air track here. It's still elevated. You can see the blocks elevating one side of the air track so that it is a downward slope. And what an air track is if I get close to it here, you can see all these tiny holes. So when I turn the pump on, what's going to happen is air is going to come through those tiny holes, creating a mostly frictionless surface. Okay, so when I turn it on, we're going to have a glider, this black thing here, and once the air is coming through the holes, it's going to make a frictionless surface, causing the glider to slide down the incline. Okay, so what we're going to do is we're going to be timing how long it takes that glider to go certain distances. So over here I have 2 timers. So these are called photo gates. So the reason that there is 2 of them is because when the glider slides down and goes through the first photo gate, it's going to start the timer. So these photo gates are hooked up to the timer shown here. So when that glider goes through the first photo gate, it starts the timer. It'll continue going until it goes through the second photo gate, which will stop the timer. So this will give us the time it takes for that glider to go between these 2 photo gates. So the distance here. So the first distance I have marked off is 20 centimeters. So for the following data points, we're simply going to move one of the photo gates another 20 centimeters so that they are now 40 centimeters apart. Then turn on the air to allow the glider to slide down the incline at an accelerated motion. When it goes through the first photo gate, the timer will start. When it goes through the second photo gate, the timer will stop, giving us the time for that distance. We will then repeat it by moving one of the photo gates to a longer distance. And that's how we're collecting the data for part C. The data shown in the table was the data collected at those different distances. And we're going to once again graph that data. Keeping in mind that time is going to go on the x-axis and the total distance is going to go on the y-axis. So this time with accelerated motion, think about what happens if you're on your bike and you're about to go down a hill. So it's kind of a similar situation. As you go down the hill, you'll notice that your velocity or your speed is constantly increasing. So the reason for this is because you are accelerating, your acceleration. So when we plot this line, what we're actually going to see is a smooth line and not a best fit straight line. So it should be more of a curved line. Now the data isn't perfect, so just do your best to make the best fit smooth line. Since it's a smooth line, since it's a curved line, there will be no slope calculation. This is because on a curved line, the slope is constantly changing. So there's an infinite amount of slopes. All right, that is everything you should need to know to finish the lab. Let me know if you have any questions. Good luck.